got a session with 4 exciting sounding talks on platform scale and fault controlled fluid flow now. I'm assuming you can hear me. Yeah, I got a thumbs up. Great. Thank you very much. Okay, so I'd like to just remind everybody, please, no screenshots, no recording. Everybody in this session has given their permission. Pretty certain that their talks will be recorded. Those recordings will be placed online. Guys, you'll have 12 minutes for your talks. I'll give you a 10-minute warning, and then we'll have 7 minutes for questions. And we've had such a great response to the questions. So thank you not only to our early speakers, but for everybody for asking such really good questions. So I'd like to move straight on now to Philip's talk. Philip is going to talk to us about a method for constraining fluid advection rates on carbonate platforms using calcium and clumped isotopes, which is very close to my own heart. So I'm very excited to hear this. Go for it, Philip. Thank you.
Fantastic. Thank you, Fiona. Thank you for giving me a chance to share this work. This is partially an outgrowth of my PhD work, but it's very exciting to have an opportunity to talk about this. And we're very pleased to announce that the manuscript for this was submitted last Friday to EPSL. So at the end of this, I'll give details, and I'm happy to share preprint if anyone wants. I have my email down there at the bottom. So as Fiona says, we're looking to constrain fluid advection rates using calcium and clumped isotopes. And just click, there we are. So the presentation, I'm going to talk briefly on a few mechanisms of fluid flow in carbonate platforms, and then I'm going to introduce the model which I'm going to use in order to simulate fluid flow, and then how we constrain recrystallization rates using clumped isotopes, and then finally we're actually going to show a data set for fluid advection rates into the platform interior. So on carbonate platforms, in this case, we're looking at the margin of a carbonate platform. There's a number of different fluid flows at play. Here we're presenting the larger scale ones, which are the reflux of evaporative brines, freshwater infiltration during glacial low stands, and the thermally driven Cahoot-style convection, wherein fluids are drawn in along the margin, geothermally heated, and then raised up, which basically is a giant auto siphon. And we're going to be looking at changes in that in response to changes in platform geometry. So how having a steeper margin means you have a stronger lateral geothermal gradient, which then increases the intensity of these convection systems. We're going to be looking at the leeward margin of Great Bahama Bank. In this case, we're going to be using site 1003 from ODP leg 166. It is interesting because due to changes in current systems in the area, in this case, the onset of these large benthic currents, you have a transition from a relatively low angle carbonate ramp style geometry. And then with the onset of benthic currents, you form these large drift deposits in the channel itself, which are shown here as a slightly darker shade of brown. And the onset of these drift deposits is at about 12 to 12.5 million years. And I've highlighted the base of these drift deposits and extrapolated it onto the site 1003. And this is coincident with progradation of the platform margin and a steepening of the slope itself. So at this site, there is a great deal of evidence of large-scale fluid infiltration. Here you can see that the uppermost roughly 50 meters of the pore fluids are essentially modern ocean. And so if you have a fluid infiltrating, it basically wipes out any other diagenetic effects. And then below this, what we're calling a flush zone, you have, due to dolomitization, you have a decrease in fluid magnesium calcium ratios and an increase in pore fluids due to recrystallization at different temperatures, the pore fluids, because it's in a more enclosed system below that depth, you tend to affect the pore fluid a great deal. On this site, again, just taking you through the change in margin geometry, you can see that the windward side of Great Bahama Bank has remained ostensibly unchanged throughout the entire history of the platform. However, the leeward margin, you can see, has transitioned from this relatively low angle carbonate ramp to this steeper carbonate steeper margin and rimmed platform style. So we're going to be looking at the effect that this transition has had on fluid infiltration rates. So in order to geochemically fingerprint fluid flow, here we're showing two figures from a recent paper by and her co-authors. And what it shows is that the difference in sediment buffered versus fluid buffered recrystallization produces a huge impact on a number of geochemical proxies. In this case, we're looking at strontium calcium ratio in the top figure and or in the bottom figure, and oxygen isotopes and calcium isotopes, which is the x-axis of both figures. And because the advection supplies lots of ions for reactive exchange, it requires a great deal of fluid flow in order to impact a more rock buffered parameters such as calcium isotopes. And so we're going to be using calcium isotopes in order to constrain the fluid rate. So just to give you a qualitative estimate of the changes before we get into the modeling, here you see, this is the actual calcium isotope data we're going to be using here on the right. You see a transition from unrecrystallized sediment in the uppermost sediment. So these are these blue dots. These have an abundance of strontium in them and return normal calcium isotope values for these sediments. Then as you transition from aragonite to calcite, as you can see in this cumulative XRD plot here, you tend towards more positive calcium isotope ratios. And then these calcium isotope ratios seem to remain for much of the sediment. But then as you go down, then you transition back to more rock buffered calcium isotope ratios, but they still preserve a great deal of their strontium. And you also see, as a more qualitative indicator, transition from more negative to more positive reconstructed fluid isotope values from clumped isotopes. So this is the general schematic of the model that we're using. You have the uppermost sediment is exchanging with seawater. Then you have some forced advection rate, which transports fluid vertically through the sediment column. Now you have carbonate that's available for reactive exchange, and the adjacent units are able to diffuse with one another following a general diffusion equation. And so what this does is this models the entire depositional history of your site. And then if you force it to have a certain advection rate, then it will output the calcium isotope ratios down core. So, and one thing that this requires is a constraint on the rate of recrystallization of these sediments. So we attempt to do that using clumped isotopes. The reason clumped isotopes works is because they are sensitive to the temperature at which minerals form. And so if we look at the thermal history of these sediments during burial, you can see why clumped isotopes are useful. So sediments form in generally warm surface waters and are then subsequently deposited into the much cooler benthic temperatures, but then are subsequently buried within the geothermal gradient. If we go back to my clumped isotope data set here, this was published in 2019 by myself and my advisor, Peter Swart, you see that you have this warm uppermost sediment. So this corresponds to the warmest unrecrystallized sediment. And then as the sediments are buried, you can see the recrystallization. And you can also see this is accompanied with a transition from aragonite to calcite in this XRD plot that I have next to the data. But then as sediments are subsequently buried, you reconstruct a geothermal gradient. Now, the rate at which it keeps up with the geothermal gradient is proportional to its recrystallization rate. And so here we see this nice transition. And in order to actually come up with quantitative estimates, we resampled our data set a number of times, and each time we fit it with a gradient descent algorithm in order to calculate the recrystallization rate parameters. In this case, it's an initial recrystallization rate, which is given as B, which is in units of 1 per million year, and the lapse rate, which is simply in millions of years. And you can see that we come up with generally decent confidence in where our bulk recrystallization rate is for these sediments. This is all detailed in the manuscript that we have in submission, but just in the interest of brevity, I'm going to continue. So these are the calcium isotope ratios. And when we feed these recrystallization rates into the calcium isotope model, we output a number of scenarios where we force advection rates between 0 and 10 degrees, 0 and 10 centimeters per year fluid infiltration rate. And so this is the output for 0. As you can see, it doesn't really change all that much. Then as we increase the number, you can see that it behaves as you might expect, where increased advection is invariably creates more positive calcium isotope ratios. But another thing that should be noticed is that no single advection rate adequately describes the entire observed variance in the calcium isotopes. So we need to create some sort of time varying fluid infiltration model. So in order to calculate the best fit values over time, we simply define 16 points. And in this case, these are evenly spaced with depth. That way they have the most, that way there's no bias in the number of calcium isotope measurements for each time point. And we allow, we create an algorithm. In this case, it's a gradient descent algorithm, which tweaks the advection rates for each of these 16 time points. And then over time, forms better and better and better model fits. This takes, on a personal computer, this algorithm takes about a day to run. Fortunately, we were given access to the ARCA cluster at Cardiff University, which dramatically sped up this process. So you then linearly interpolate between these points. And then, as I said, you use a gradient descent optimization process. This takes an initial guess, and our initial guess is just that there's no advection, and then it gradually increases these values until it finds a best fit. And then we repeated this process 160 times using a bootstrap resampling of our data set. This just lets us know what impact the variance in the calcium isotope measurements has had on our estimated fluid advection. So let's look at the final data set. As you can see, the model very nicely captures a lot of the larger features in the calcium isotope data set. And as you can see, there is very little advection up until about 12.5 million years, at which point there's a dramatic increase to about 15 centimeters per second. And then it peters off, but never goes to as low as it was prior to this pulse, this initial pulse, with a few small points that I'll discuss the reasons why we think those exist now. So as you can see, there are a number of hiatuses in our data set. This one up here in particular, this 8.7 to 6.2, this is the longest hiatus we have, and it corresponds to a fairly significant jump in model values.
Less than 2 minutes left.
Less than 2 minutes. Oh, sorry. I'll be quick then.
Yes,
The transition, the change in calcium isotopes correlates with the transition from aragonite to calcite. I'll be faster. And there's a general transition in the sedimentary record from wacky stone to pack stone, which could be increasing the fluid advection rate, although this is unlikely because the permeability of these sediments is largely driven by the micrite, which is always present at the site. So it's always muddy. The larger particles don't necessarily affect the permeability of these sediments.
Could you just conclude now?
Concluding,
thank you.
Yeah, we show exactly as predicted a major pulse in advection, which corresponds quite nicely with the estimated onset of these benthic currents and the transition from a carbonate ramp to a steeper margined carbonate shelf. I think I can just leave it there. Thank you for listening. This is the details of our submission to EPSL. I can send you a preprint if you'd like.
Thank you very much, Philip. So I think we'll wait for a few questions, and basically I'm going to take the luxury of being able to ask the first one, which I was wondering, in your initial slides, you were suggesting that during periods of low sea level, when you have a freshwater lens developed, you're less likely to have active Cahoot convection. I'm wondering why you thought that was the case.
Well, it is if you have the reason when we're looking at our data, you see from this point number 2 here, you do see a transition towards lower values as you enter into the Pleistocene. We speculated that the formation of freshwater lenses periodically during sea level low stands might decrease the absolute value. There's also reasons to think that refluxed brines might also have a similar inhibitory effect. But with the data as we currently have it, it is just speculation. You're correct. We're simply calculating advection rates on the margin. The actual underlying driving force would require more nuanced models, such as the ones which you occasionally, which you have put out a number of papers on. You are mentioned a number of times in the manuscript.
Sorry about that.
Oh no, it's fine.
Do we have any more questions? I mean, I have lots of questions, but I don't want to dominate things. While we're waiting for those questions to come in, can I ask you another one?
Sure.
So you based your analysis on these 16 data points, and obviously processing that data takes quite a lot of computer power. But that's assuming that you've got some sort of systematic change with depth, right? Mm-hmm. Now, I would have expected the variance in some parts of the system, like the calcium isotopes, which you do take into account, to be small relative to the variance in permeability in this system. So I'd expect the flow to be focused in specific permeable zones rather than to have a systematic change in the behavior down section. And I wondered if you saw any relationship between the permeability of the sediment and the calculated advection variations.
Yeah. Well, I do have the sediment column here, and these pulses, or at least this first pulse, does correlate with this transition from these muddier sediments further down up to these coarser wax stones and pack stones up here. So you have a transition from mud to a more potentially permeable, even though interparticle permeability is, the actual permeability is governed more by the muddy matrix which the various alchems are floating in. But you're right that there is this trend towards potentially more permeable, and then that is accompanied with the single largest increase in advection rates that we calculate. But I think to answer your question, a better approach might be to look at a muddier site. Find another, take another core on the margin and analyze it down core much in the same way we just have. There are other cores that we could look at, and in fact there are calcium isotope data sets that exist, but we would need to produce the clumped isotope data set in order to adequately constrain the reaction rates for that site.
Sure. Thank you. We've got a question in from Cedric John, who says, great talk, Philip. Perhaps you said so, but do you assume that 100% of your micrite is recrystallized at each time step for your clumped isotope signal? Or is a mixing between different phases likely?
Trying to understand. So he's asking, is the micrite more recrystallized than the...
He's saying, are you assuming that all of your micrite is recrystallized at each time step?
No. We model this with such that over the time step, a certain fraction of it recrystallized, which is proportional to the reaction rate. If I can go back to my plot here. So the rate of recrystallization is on the order of 1 per million year initially, and then it slows down considerably over time. And the rate of that slowdown is informed by the difference between this reconstructed geothermal gradient that we calculate using clumped isotopes and the actual measured geothermal gradient at the site, which is about 30 degrees Celsius, 35 degrees Celsius per kilometer. So that's the rate at which bulk recrystallization is modeled. We don't separate the micrite and coarser phases in this model.
Okay, thank you. I think we're out of time, but there are some more questions coming in. So I think it would be great if we could continue discussion maybe in one of the breakout rooms at lunchtime. So I'm going to move on now to our next speaker. Thank you very much, Philip.
Thank you.
And our next speaker is Cathy Breislin. Cat has slightly dodgy internet, so we won't see her beautiful face, but we will be able to hear her. And she's going to be giving us a talk on controls on the localization of fault fracture controlled dolomitization, insights from the Derbyshire platform, Lower Carboniferous UK. So please do go ahead, Kat.
Hi, I hope you all can hear me okay.
Yep,
I'll start by saying I have approximately a 3-second delay between my slides, so I'll try and keep up with that. So today my talk forms part of my PhD work, which I completed at the University of Manchester. And today I'm going to focus on the controls and formation of fault fracture controlled or hydrothermal dolomitization on the Carbonate platform, in this case focusing on the Derbyshire platform in the UK. I'm going to talk through the distribution of the dolomite, the style of the dolomitization, looking at the petrography and the geochemistry. I'll also talk about the relative timing of this dolomitization in relevance to the burial history of the basin, and I'll also discuss the fluid source. So in this slide we can see a Tectono-Stratigraphic map of the UK and the Carboniferous. On the left hand side in A, where we can see the carbonate platforms, which are in the blue, and the basins, which are in the grey. These thin rift carbonates were deposited on the stable blocks during the Carboniferous, during the Bacian, which is in the Mississippian, and on B we can see that development of the carbonate platform of the Derbyshire platform was from EC3 to EC6. Back to the left hand side we can see the red arrows in the Tectono-Stratigraphic map, and these point to where dolomite bodies have developed on the margins of these Carboniferous platforms, with the Derbyshire platform highlighted by a yellow box. Most of these dolomite bodies are fault controlled and they vary in form, forming stratobound and non-stratobound bodies. All of them, however, do host calcite, fluorite, barite, galena, sphalerite mineralization, which post-date the dolomitization. For the Derbyshire platform, a paragenetic sequence framework had been created through the work of Hollis and Walkden. And this takes in the calcite cement phases, which go from platform formation through to burial and inversion. So we can see the calcite cement phases are at the top, which go from 1 to 4. The most important phase to highlight here is the phase 3A, and this is a meteoric calcite cement, which included much of the porosity on the Derbyshire platform. So now we'll look at the distribution of the dolomite. On the geographical map on the right hand side, the carbonate platforms are in grey. We also have the northwest southeast faults, which are in black, and these are the main platform bounding faults. So these are active during the platform growth, and are also active during basin inversion and allow the fluids to flow. What we can see is on the southern margin of the Derbyshire platform, we have two main geobodies, dolomite. One is proximal to the platform margin, which is labelled as D1 in a lighter green colour, and one is orientated along one of these northwest southeast faults, which is labelled as D2 in a darker green colour. Dolomitization on Derbyshire platform is multi-phase, and an earlier phase of dolomite, which is the D1, the lighter green colour. This formed during the early platform, just before it was buried, and this is a replacive phase and forms approximately 50% of the volume of the dolostone you see on the platform. This isn't discussed in the talk, but I'll be referring to it later. The main phases we're looking at, which are the fault controlled phases, the hydrothermal dolomites. This can be seen as the D2, the dark green colour, which goes along this northwest southeast fault. This D2 phase is non-stratobound. It's a replacive phase and it forms approximately 40% of the dolomite we see on the platform. Another phase which can't be mapped because it's so small is the D3. This is also non-stratabound. It's orientated along north-south faults and forms less than 10% of the dolomite volume. Two final phases, which are form of cement within fractures. Again, these can't be mapped because they form less than 5% each, but these also form along northwest-southeast faults, north-south faults, and northeast-southwest faults. On a dolomite platform, all phases of dolomite are crossed by calcite, barite, galena mineralization. Now we'll look at the dolomite front, so what the dolomite looks in the outcrop. So this is the D2 phase, our main fault-controlled hydrothermal dolomite. On A on the left-hand side, we can see the outcrop photo, which is slightly enhanced. So you can see where we've got the grey colour is where we've got the limestone, and where we've got the brown colour is where the dolomite is. So conveniently on B, I've highlighted these, giving a green colour for the dolomite. And we can see these faults which I've drawn in here in fractures, and these are these northeast-southwest orientated faults and fractures. Dolomitization occurs preferentially within the lower clay content beds, and then where dolomitization does occur, it fingers out into stratabound fingers which extend laterally away from the faults. We have partial metic replacement of the alicums and a non-planar to planar dolomite fabric formed. Also within the faults and fractures, occasional zebra dolomites have been found, as well as later hydrothermal calcite and barite. So moving on to the D3 dolomite, this is the phase which only has about 10% of the dolomite. And again, on the left-hand side, we can see the outcrop photo, and then in B, we can see the overprint. So here we're looking at north-south orientated faults and fractures. And then the halos which the dolomite formed are much smaller, so we're looking at 5 centimetres to a metre extending out from these faults, with larger faults generally tending to have wider halos. The bottom photo on the right-hand side, we can see the front of the dolomite is, and these are very sharp fronts as well. These are not diffuse. So looking at the petrography of the dolomite, back to the main phase of the dolomite, which is aligned to the northwest-southeast faults. It's fine to coarse crystalline, non-planar to planar dolomite. It's usually very inclusion-rich, and cloudy core to clearing fabrics can be developed towards the dolomite fronts, where it becomes slightly more mimetic. This phase contains 2 phase fluid inclusions, and it cross-cut stylites, as we can see in the top photomicrograph. The D3 dolomite, which is found along the north-south fractures, is very similar petrographically to the D2. It also forms planar to non-planar dolomite crystals, has 2 phase fluid inclusions, and in the bottom in the PL and the CL images, we can see there is a slight difference in the luminescence where it is overprinting this D2 dolomite. The final phase of the dolomitization, D4 and D5, and these are fracture-confined cements. These are found only in fractures, particularly hydrofractures, as we can see on the right-hand side images, where we often have these 2 different cements filling void space. The D4 is the pinky coloured non-planar dolomite cement which surrounds the clasts, and your D5 is the white planar solid dolomite crystals which can partially to completely fill the fracture void space. These 2 dolomite cements are followed by a fluorine non-luminescent hydrocarbon phase, the C44B, as identified by Cathy Hollis, which is in the photograph D in the bottom left. And then after that, the 4C calcite cement, which is the bright orange luminescent phase. These 2 phases are associated with fluorite mineralization, which is associated with fault reactivation and mineralization from downward fluid flow from the overlying shell seals. So that's just one of the last phases of mineralisation on the platform. Looking at the geochemistry of the dolomite, we have the phases D2 to D5. The plosive phases, which are the D2 and D3, which form the bulk of the hydrogel dolomite.
This is your 2-minute warning.
Okay, thank you. Are highlighted in red and have very similar carbon signatures to the sea and marine carbonate. The D4 and D5 cements are highlighted in the yellow, and these also have a very similar signature, but slightly more enriched. Compared to the marine carbonates, all dolomite phases have an enriched delta 18O water. However, overall, it appears there's been rock buffering, indicating that the fluid rock ratios were sufficiently high enough to preserve the signature of the dolomitizing fluids. Looking at the strontium isotope signature, we can see the D2, D3, D4 and 5 again show the rock buffering of the carbonate signature. However, we are more enriched in strontium, suggesting that the dolomitizing fluids have interacted with siliciclastic sediments. Fluid inclusion analysis shows that the dolomitizing fluids have high temperatures which range from 83 to 148 degrees Celsius, with moderate to high salinities which are approximately 4 times the amount of seawater. There's a range in the salinities across all of the dolomite phases, and the relatively consistent temperatures could either result from rapid fluid expulsion of the basement and then placement onto the Derbyshire platform, indicating that the 4 phases are very close to each other in formation, or potentially a blanketing effect from the formation under a shale. This analysis allowed me to refine the paragenesis of the Derbyshire platform, with the D1 dolomite forming much earlier during the Sinriff period, and then the main phase of dolomitization, your D2, and then D3, which are replacive hydrothermal. These form in the post-drift towards the inversion, and they occurred post the porosity occluding cement of the platform.
Okay, we're reaching full time.
Please. Okay. So to conclude, this study shows that there's an interplay between kinematics and the host rock permeability and the timing of the fluid supply, which is supplied through forms of the platform. The distribution of the Derbyshire platform, along with the chemistry, indicates the specific timing and conditions which the Breislin brines are connected, controls the positioning of the dolomite bodies. Thank you for listening.
Thank you very much, Kat. That was great. Okay, so we're just waiting for some questions to come in now. I have a question. I can't remember the exact figures you were discussing, but you were talking about your later dolomites, I think being 3 or even 4 times the salinity of seawater. Is that correct?
Yes, yeah.
What do you think is the origin of those high salinity fluids?
So the most obvious source would be the basinal brines. But the very high salinities could also potentially occur with a mixing from a different basinal fluid as well, because there's quite a significant range in what is observed. Another reason for the range as well could also be the lower salinities may be reflecting mixing of these dolomitizing fluids with interstitial pore fluids which were left on the carbonate platform as well. So that could result in the range we have.
Okay, thank you. So do you think some of your higher salinity basin fluids, so you're saying, well, they're coming from the basin, but how did those high salinity fluids get into the basin? Were there episodes when circulation was restricted and maybe the seawaters within the basins became concentrated by evaporation?
It's possible. We also have underlying evaporites as well, which may have contributed to this. And the part of the platform, there we go. Part of the Derbyshire platform that we're looking at, if we see just below the platform, the Benjakul Gulf, it's a relatively restricted basin, so it is possible that there could have been some slight restriction of this basin and an increase in the salinity.
Okay, that's great. We're still waiting for a few questions to come in. So can I'm really sorry to ask you another one, but can I ask you another question? So if you're invoking those higher salinity fluids from periods of restriction when we're precipitating presumably gypsum, which has then gone on to form anhydrides, those fluids wouldn't be particularly rich in magnesium, would they? If anything, they'd be calcium rich.
Yes, yes. But I suppose mixing with, if this occurred towards the end of the basin fill, it's possible there was sufficient minerals clay minerals within there to provide the magnesium as well.
Okay, that's great, thank you. Some reason my view of the chapters has gone completely wrong, so bear with me 1 second. There we go. So we have some questions. We have one from Mumtaz who says, great job, Catherine. Can you explain your D2 phase showing depleted Del 13C? Do you have petrographic evidence to support these depleted values?
So the D2 with this slightly depleted, so looking closer to 0 to 2. This could be the result of overprinting of the early Dolomite phase, which we see the dark blue squares below in D1.
Ah, sorry, he's saying, sorry, I meant the D1 Dolomite.
The D1, okay. So this is an early phase of Dolomitization, which occurred just prior to platform burial. And these negative carbon signatures, I do apologise, they are spotted around the labelling on the graph, but the negative carbon signatures are associated with mixing with volcanic geothermal fluids, which have a more negative carbon signature.
Okay, the questions are coming in thick and fast now, so I'm going to try and speak them fast. Christine is asking, beside the dolomitization, is there any orthogenic clays, for instance, illite?
Not observed on the carbonate platform now. Yeah.
Okay, can I move on to the next one? Try
yes,
and get many of these. Martin Nowak is asking, the brownish colours in, he says, thank you, very nice talk. The brownish colours in outcrop pictures might indicate a high proportion of iron, which might also be indicative of de-dolomitization.
So I did enhance the photos slightly so you could see them. In outcrop, they are slightly a buff colour, but yes, there is some iron staining. And I've not included it in this talk, but I've also looked at dolomitization within the basin, and there we do see hematite staining and quite significant amounts of hematite within the basin. So again, these hematite could have come up onto the platform via the faults.
Okay, and do you also see de-dolomitization? That was the second part of the question, I think the critical one.
Yes, yes. So there is de-dolomitization, and it's particularly associated with these mineralizing fluids. I'm sorry, someone's at my door.
That's all right, we're out of time. I think what we're planning to do is have a breakout session at lunchtime focused on fluid advection in carbonate systems. So it'd be great if you could join us for that.
Brilliant, thank you very much.
Thank you very much, Kat. Right, so we're now going to move on to our next speaker. And our next speaker is Tan, or Rungroj Benjakul, fortunately known as Tan because I can get my mouth around that more easily. Tan is going to talk to us about high temperature fault controlled dolomitization by convection of seawater, a concept evaluation using reactive transport models. So, Tan, if you could turn your screen on.
Can you hear me?
Your screen. Yes, we can hear you. please do go ahead.
Yeah, right.
Talk. Thank you.
Yeah, thank you, Fiona. Yeah, thank you. And hi, everyone. In this talk, we are focusing on formation of fall-related high-temperature dolomites and evaluating role of seawater as magnesium source. The hydrothermal dolomites form at high temperature and show strong structure control, forming along extensional or style slip faults. Here, we see the importance of hydrothermal dolomite within wider context of low temperature sedimentary hydrothermal mineral association, both at a host for Mississippi Valley type sulfide deposits and often in association with dissolution and reservoir for oil and gas. So most widely cited conceptual model for hydrothermal dolomite formation is that of Davy and Smith, 2006, which rely on deep sort of hot magnesium-rich buoys that ascend along fault, driven by buoyancy and release of overpressure. So this upward movement of fluids has become very much in dominant paradigm in understanding hydrothermal. For example, inlet Cretaceous from the Menicasm in Spain at your left-hand side. So the conceptual model are all really well, but how do we evaluate this paradigm? The first thing we can do that we can use the fluid flow model, which show hot fluid can ascend fall rapidly with lateral flow into permeable unit. And we can also model reaction where injection of hot magnesium-rich fluid called Dolomitization adjacent to the fault, or literally where a seal prevent upward flow. However, this model all rely on the hot fluids coming from the deep surface, and it must have the availability of large volume of magnesium-rich fluid at depth. But how do we know that such fluid exist? So we have investigated the dolomitization potential of deep buoys from USGS database, and we found that most of them contain far less magnesium and calcium than modern seawater, as well as the magnesium and calcium ratio, which means these deep buoys have low potential for dolomitization. So it is hard to form hydrothermal dolomite from deep aquifer fluid. What the alternative are there? And you can see from the diagram, it is obvious that the alternative fluid source is seawater, available in very large amounts, and is rich in magnesium with a high magnesium-calcium ratio. Previous work in the Gulf of Suez left a high enthalpy setting with a current geothermal gradient of 47 degrees Celsius per kilometer. We have characterized massive dolomite body formed within the damage zone of the Hamar and Faroon fault, which you can see in the diagram on the left-hand side. The conceptual model we came up with to explain this was convection of seawater within the fault zone driven by heat flux. As the seawater provides magnesium, you don't have to rely on the magic hot fluid from the depth. You can see that this is a nice concept and was supported by geochemical and isotopic data. However, the question are, how realistic is this idea, and is this model capable to form large-scale dolomite? To evaluate this concept, so we have used reactive transport modeling, or RTM. Some of you might not be familiar with the RTM. The RTM is essential tool for the analysis of coupled fluid flow and geochemical reaction in Earth system. It can applicable at a range of spatial and temporal scales. It also incorporates the really important feedback between fluid flux, heat, and solute transport, reaction, and also log properties. So this tool has been applied to the study of dolomitization, but mostly focused on the shallow low temperature system, such as the reflux system, and also platform scale geothermal convection. But for our study, very simple numerical model is constructed to test the concept of dolomitization by top-down convection of seawater in a single transmissive fault system. the permeable fault damage zone, hereafter called FDZ, and is displayed in red. The top boundary is open to the exchange with overlying seawater at 25 degrees Celsius, and the basement of the model is set at 250 degrees Celsius. So this will giving an initial geothermal gradient of 45 degrees Celsius per kilometer. The cap rock and the basement are unreactive, and the aquifer is calcitic with only 1% of dolomite, which we will model it as a kinetic mineral. The simulation both in 2D and 3D were conducted using tablet. So now let's take a look at the result. The 2D simulation perpendicular to the fault show that the FDZ acting as a conduit for advective discharge of hot fluid from the basement is at high flux of hot fluid within FDZ, but delayed, at which magnesium-rich seawater is entrained to the matrix is low, and the dolomitization is negligible. For the 2D model along the fault, it shows convection of lot of magnesium-rich seawater within the FDZ, but it's maintained temperature that are too low for dolomitization to occur. So both 2D models suggest dolomitization potentially very limited. In contrast, the 3D simulation clearly demonstrates the importance of considering both flow along the plane of fault and heat exchange within the surrounding matrix. The fluid flux is strongly focused within the FDZ, and high temperature at the basement leads to the upflow of fluid throughout the aquifer. The lower permeable of the cap rock forced the ascending fluid within the aquifer matrix back into the FDZ at the depth shallower than 2.5 kilometers. Seawater is drawn into the FDZ, resulting in cooling that extends to considerable depth and laterally into the surrounding matrix. And we can see that most fluid flow occur within the FDZ, but comprise a mixture of seawater supplying the magnesium for dolomitization and a significant component of the basement water which maintain temperature that are kinetically favorable for dolomitization. So here in this animation of the 3D simulation on your left-hand side, you can see how the flux of magnesium-rich seawater across strong thermal gradient and how it's controlled the distribution of dolomitization. Initially, the rate of dolomitization is pretty low, but accelerate over time. This increased the porosity and permeability so that after 15,000 years, more hot water is drawn into the fault from the matrix and entering dolomitization in the Darwinian core. The fluid flux and dolomitization is limited to the fault damage zone with minimal alteration of the low permeability matrix, as you can see on your left-hand side. Most of dolomite formed by replacement of calcite with maximum of only 5% of dolomite cement. Therefore, we see pattern of dolomitization echoed by porosity here at 15,000 years. And if we look closely at the selected location in the fault damage zone, with distance laterally away from the Darwinian core at A and B, C point, and vertically to the core from A, D, and E point, we found the temperature at the base of fluid fraction of dolomitizing fluid is consistent throughout the reaction progress at different locations. However, at some location, we see a step change in dolomitizing fluid with the additional more warm water derived from the basement and delivered via the matrix. So this change occurs because the flow and heat transport behavior evolved through time. As you all know, it's difficult to model flow in fault because we don't really know a lot of conditions within the fault. So we can imagine doing really wide speed of models. In here, we just illustrate this by representing one alternative scenario. Here we are changing the flux of basement fluid by lowering the permeability of the basement. Everything else in this model is exactly the same. So what we can see here is a significant change both in the size of the Dolomite body and how quickly they form.
2-minute warning, Tan.
Okay,
Thank
gonna
you.
be quick. We also have the same influx of seawater supplying magnesium, but less hot fluid coming from the basement. As a result, the whole system is a lot cooler and less dolomite, as you can see from this diagram. So to summarize, there are 4 key take-home points for you. First, the convection of mixed fluid along the FDs can form sizable fall-bound dolomite bodies within thousands of years in high entropy setting, with seawater providing critical magnesium and heat from basement allowing relative rapid dolomitization. And we can also interrogate the RTM output to give us other useful information, not just on the shape and size of geobody, but also on temperature of dolomitization and the source of fluid. It's also important to model this system in 3D. The 2D model failed to represent interaction between the fault and matrix, and therefore will give misleading results. And finally, we can apply the same technology to understand other fault-related diagenetic reactions. For example, the mineralization and the modification of porosity permeability during diagenesis. And the next step for this study is to investigate the chemical controls on this mechanism. For example, the different fluid composition between seawater and brine to evaluate the potential for dolomitization. And then we will develop a more realistic model to exemplify the natural systems such as relay lamp structure. All right, thank you everyone very much for listening.
Thank you very much, Tan. Right, now I normally hold the fort at this point, but as I'm a co-author and I've heard this multiple times, I'm going to ask for all of you enthusiastic people, please, to get onto your keyboards and send me some questions, because I'm sure Tan can expand on some of those points that he's been making. Right, great, thank you. Cole, we have a question from Cole McCormack saying, hi Tan, excellent presentation. You mentioned in your model that about 95% of the dolomite is replacive. What Cole would like to know is, does this change at all over time? And as the model persists, do you ever achieve more than 5% cement?
Okay, all right. Yeah, that's a good question. Let me show you in my backup slide. Sorry for the delay. Yeah, so we have tracked the process of the replacement and also cementation, and we found that at some selected location, for example, at the B point, so we have a high replacive dolomite starting from, very early at about 3,000 years. But however, we never have, the cementation more than 5% in every point. So that's why we conclude that most of the dolomite here are formed by the replacement process. And that's why we have less than 5% of cementation. So from the figure, you can see, the volume fraction of the replacement dolomite display in the yellow color, and the dolomite cementation displayed by the blue color. And you can see the contrast between the replacement and also the cementation from this selected location.
Thank you, Tan. We have another question from Cathy Hollis, who says, thanks, Tan, for a great talk. Could you say a little bit more about how far fluids move away from the fault into the matrix?
All right. So yes, from this figure, you can see that when we have the seawater entrained into the downwelling core, and then it goes down until it meets the low permeability of the basement, the fluid start to migrate lateral, and then it's gonna transfer into the matrix zone and mix with hot fluid from the basement, and then it can go laterally into the matrix. And I would say that it can go until it's meet, the boundary of this model. So that's why we try to generate a distance.
Okay, we've got a few more questions, quite a lot of questions. We will have a session at lunchtime on this. We've got 3 minutes left for questions. Jack, Stacey has a question. Thanks for a great presentation. Really interesting that basement-derived fluids are so important. Do you have any thoughts on what these fluids are? Are they simply basement interacted seawater, or are they basin brines?
Yes, from our model, we use 2 different fluids in the simulation. So the first one is seawater at the top, and then we have the basement fluid, which is a brine at the bottom. But the basement fluid is equivalent to both calcite and magnesite. And from this figure, you can see the mixing of seawater and this deep fluid, and you can see that most of the fluid that circulate in my 3D model composed of about 50% to 80% of the basal fluid from the basement. And that's why we will do the next step for we have to simulate the different type of deep brines that could help us to understand more about the role of the missing fluid in hydrothermal dolomitization.
Okay, thank you. And we have a question from Volker Vankamp, who said, great talk. What was the width of the damage zone, and did you model sensitivities on fault damage zone width?
And unfortunately, we didn't do the sensitivity on the damage zone width yet, but for this model, we used it at about 80 meters of fault damage zone. Yeah, but we can do that. That is one of the uncertainty in this model, and it's really interesting to do that. So we will keep that in the next step.
Okay, thank you. I'm trying to get through all the questions. We have one from Raphael, who said, really nice work. Could you say anything about the implications for the relative volume of dolomite through the geological record?
Yes, that interesting question as well. So we have compared our simulate model site with, in the dolomite in the nature system, and we found that from our model, you can see the size of dolomite expand in the scale of 100 meters. So it's the same size as some massive dolomite that we found in Hamman Farun Fall, or also in some area like in northern Spain and Italy. So I would say that the scale is in the same magnitude, but as we don't know, in the real system, we don't know. We cannot see the whole outcrop, so it's hard to say.
Thank you, Tan. We're out of time for questions now. So we're going to move on to our last presentation. This is a poster presentation. So it will be a 5-minute presentation from Eduardo Fiordalisi, I do beg your pardon, Eduardo, from the University of Manchester. And Eduardo is going to take us through his poster, which is available on Seds Online. And I assume you're going to share your screen, Eduardo, so we can see the bits of poster that you're talking about at a particular time. So Eduardo is working on reconstructing fluid circulation pathways in volcanically influenced settings. And this is a case study from the Namib Basin of Angola.
Yeah, just check.
So we can see your face. We'd love to see your screen.
Yeah. Cool, just 1 second. Cool, you should be able to see my poster now. Right, hi everyone. My name is Edoardo Fiordalisi, PhD student at the University of Manchester, and my research focuses on fluid flow in volcanically influenced settings, taking as a case study the Namib Basin in Angola, which developed as part of the South Atlantic opening, and where in the post-rift sequence, we have the occurrence of continental spring carbonates developed following renewed tectonic and magmatic activity, making this a very good interval in order to study plumbing systems, fluid sources, fluid rock interactions, and mechanisms leading to carbonate precipitation in volcanically influenced settings. As we can see from the field, we can see that the spring carbonates commonly occur in close proximity to faults and are characterized by distinctive vent areas from which water used to come to surface, rapidly precipitating calcium carbonate upon degassing, but also flowing laterally, feeding the slope system, and fauna-rich pools downstream, as shown in this depositional model, which possibly evolved into a fully lacustrine environment with the formation of the topmost pinnacle morphologies, like shown here, as they are believed to be indicative of a subaqueous environment. Petrography integrated with other techniques such as XRD and, as in this example, EPMA mapping, suggests that all fascies are all pervasively dolomitized, with dolomite being preserving, but also occurring as dolomite cement overgrowths. While isotopic data of dolomite matrix suggests that the genetic fluids have a meteoric to slightly saline origin and are derived, possibly derived from infiltrations through soils, as suggested by the mostly negative carbon, and were heated later. And we can see there is a temperature trend revealed by the oxygen isotopes, while clumped isotopes suggest temperatures between 32 and 55 degrees. Strontium isotopes also suggest that these fluids circulated through surrounding magmatic deposits, in this case the Sin Rift volcanics, as they've got compatible signatures. Finally, after the dolomite, we have a phase of intense fracturing of carbonate fabrics and precipitation of silica, with silica both occurring as matrix replacement and also cement sealing the fractures. And fluid inclusion in silica crystals suggests temperatures up to 260 degrees, which might relate to a later and stronger magmatic pulse. Thanks very much for your attention, and please come to my breakout room for further discussions.